Welcome back to College Algebra. Today we're going to be looking at section 7.1, Systems of Linear Equations. This is the last chapter that we're going to be doing, and we're only going to be doing 2 sections from it. So you only have a couple more videos left before we're done with this class. A quick note, you will have homework over this section, but you won't have to take a test just on this section of the book. It will be included in your final exam, but it's not going to be a specific test on chapter 7. So just think about that as you're studying. And let's go ahead and get started. Our scripture for today is just an encouragement that whatever you do, work at it with all your heart as working for the Lord and not for men. Colossians 3:23, which is to say whether you're a freshman or a senior, whether you're about to graduate or just getting started, you're working on college algebra, or you're serving in your church or at your house, whatever you find your hands to do it with all your heart as a service to the Lord. So we're going to do just that, but with systems of linear equations. The first thing to notice is this is going to be real similar to chapter 4 when we talked about linear equations. It's just going to be putting 2 of them on a graph. And so you can put 1 linear equation on a graph, which means you can probably put 2 on the same graph and see there's only 3 things that can happen. They can intersect once, which makes them an independent system. They cannot intersect, which makes them inconsistent. You might also know those as parallel lines. Or they can be dependent or coincident lines, which kind of means that they are the exact same line, even if they look a little bit different as they're in their formula format or in their equation format. They may look different, but it's 2 lines that are exactly the same line and on top of each other. All right, so we're going to get started by just verifying a solution and seeing if something's true. And so here we have a point. Remember, all points are x comma y. And so to verify that this point is true, we're just going to plug and chug it in and see if it's true. And so we have 5x minus 4y equals 20, which means I'm going to plug those points into x. So 5 times 8 minus 4 times 5 equals 20. And see if that's a true statement. 40 minus 20 equals 20, which means 20 equals 20. And so that first statement is true. But it's not enough for one statement to be true. They need to both be true. And so we're going to do a second statement and see if it's true. So we'll say 2x plus 1 equals 3y, which means 2 times 8 plus 1 equals 3 times y, or 5, which means 17 is equal to 15. And is that true? That is not true. 17 does not equal 15. That's false. And therefore, 8 comma 5 is not a solution. They would have both had to be true, like in the first green equation, for it to be a solution. But this is an example of them giving you a point to plug and chug. Let's see what happens if they don't give you a point and they just give you 2 equations. What we're going to do is we're going to graph these 2 equations using the skills from chapter 4 to just see what happens. And so the first thing I'm going to do is I'm going to split these up into the blue line and the red line. And I'm going to say the blue line is 2x minus 5y equals negative 25. And if you remember from chapter 4, the way we did this is we just solved for y. So negative 2x minus 25. I moved the 2x over. And then I'm going to divide by negative 5 on the entire side. And so y equals 2 over 5x. There's my slope. Plus 5. There's my y-intercept. 0 comma 5. And so for the blue line, I'm going to go up here and I'm going to plot a point 0 comma 5 because that's my y-intercept. And then I'm just going to use rise over run up 2 over 5, up 2 over 5 to plot a few more points. So up 2 over 5, up 2 over 5. That was 4, 5. And then I'll go the other way too. So over 5 down 2. over 5 down 2, just to get every point possible. And I'll put a blue line across all those points and say that blue line is the first equation. It's a linear equation with a slope of 2 over 5 and a y-intercept of 0, 5. Then we're going to do the same thing for the next one. And we're going to solve for y. And so y equals 4x plus 35 divided by 5. I was doing 2 steps at once. I moved the 4x over and I divided by 5. Now I'll split it up and say 4 over 5x plus 7. And there again we have a slope of 4 over 5 and a y-intercept of 0, 7. And so I'm going to go up to 0, 7 and put a red dot. And I'm going to say I'm going to go up 4 over 5, up 4 over 5. You'll notice if we try to do it once, it doesn't work because there's no point there. And so I'm going to have to go backwards. I'm going to have to say if I went over 5, I'll have to go down 4. Over 5, down 4. And then you can check it by going forwards again. Up 4 over 5 works. Up 4 over 5 works. And I'll draw that red line. And you can probably see already where these intersected at if you looked at the point that was in common, that green point right there. So it looks like these two lines intersected at -5, 3. And so that's your solution, or your place where they intersect, which means these two were independent. What do they call them? Not lines. Independent system. It was an independent system with a solution of -5, 3. And so one way you can solve these is by graphing each line and seeing what happens. A second way you can solve these is with substitution, which is using the properties of variables and just kind of sliding some stuff into other variables. So you see here, this one really works when a variable is by itself, or it's really easy to get by itself. And so you see there's an x right there, and there's also an x right there. And so what I'm going to do is I'm going to take that x value and plug it in, and say I have 4 equals 3, and instead of x, I'm going to write y plus 3, because technically that's the exact same thing as x, based on the first equation, minus 2y. And so what did I do? I took the second equation and I plugged the first one into it. And then you just solve for y. So distributive property, 4 equals 3y plus 9 minus 2y, which means 4 equals 3y minus 2y is 1y plus 9, which means y is equal to -5. But we're not done with our solution, because if you remember the other one, the other solution looked like a point. And so what we need to do now is pick either of the two equations and plug it back in. So I'll take the first one because it seems to be a little easier to plug and chug. And I'll say if I know that y is -5, that means x equals y plus 3, which means x is equal to -5 plus 3, which means that x is equal to -2. And there's my solution. -2, 5 is a solution to these equations. So you can substitute by taking a variable and plugging it in. You can put them on a graph, and you'll get the same solution if you do either of those two things. A third way is by the addition method, which just says we're going to add both equations together. But before we do that, if we were just to start adding these, we'd get something like, if we put a plus sign here, we'd say this is like 5x, and that's like -6y, and that's like -18, and that's no easier to solve for us. And so we need to do something first before we add. What we want to do is we want to multiply both sides by something, anything, that will make one of the variables cancel. And so if I look at that y value, I say I'm only 7 away from canceling. And so I'm going to multiply by 7 on the top and the bottom. And what I'm going to get if I distribute that is 21x plus 7y equals -140. And so that's the same line as the red one. We just multiplied by 7 on both sides. And what I can do now is take this first one, this blue one, and write it underneath it. And I'm just going to add both equations together. Really what you could be saying is you could add the left side and add the right side because you can't add across an equal sign. And if we do that, we get 23x, the 7y and the negative 7y cancel, equals negative 138. Which means x is equal to negative 138 over 23. Which if I had to guess, that's probably going to reduce. Let's grab a calculator real quick and say 138 divided by 23 is 6. And so x is equal to negative 6. But again, we're not done. We've only found the x value. We need to also find the y value. So you pick either of those two equations. Again, the blue one looks a little bit easier, so I'll use that one. 2x minus 7y equals 2. But I'm going to say x isn't x anymore. I'm going to let x be what I know x is, which is negative 6 minus 7y equals 2. And then I'm going to solve for y. So negative 12 minus 7y equals 2. Negative 7y equals plus 12 to both sides. You get 14, which means y equals negative 2. And so your solution here is both of those points when you combine them. Negative 6 comma negative 2. Try it 5. Looks like it's just addition again. So I'm going to let you try that on your own. But what I want you to notice here is things aren't really easy to see how they cancel. And so what I would offer to you as you try it by yourself, pause the video if you need to, is to say, what if we multiply the top by 3? So I multiply all across the top on both sides of the equal sign by 3. And I multiply the bottom. So 3 times 2x is 6x. And I'm going to multiply the bottom by negative 2. And what you're going to see there is on the red term, you're going to have a positive 6x. And in the blue equation, you're going to have a negative 6x. And then you're going to be able to add them with the x's canceling to solve for the variable. And so let's try it 5. Give it a shot. Pause the video if you need to. And you can go and look at the solutions online if you're having trouble with it to look at what the next step might be. All right, we need to look at some of these other types of systems, the inconsistent systems and the dependent systems, to kind of see what they look like when we plug and chug them in. So we want to solve these equations. The nice thing is they've already set it up for us, so something will cancel. So what I'm going to do is I'm just going to multiply the bottom by negative 1. And so what I get on the red equation would be negative 2y, distributive property, plus 2x equals negative 6. And then if I bring down this blue equation so that I can add them, I have 2y minus 2x equals 2. And then I'm going to add both sides. You might have seen this called subtraction before, where you subtract two sides from one another and you don't multiply by that negative. That's okay too. If you've done it that way, that's an okay way to do it. I just am showing you addition because that's the way the book's shown every problem. And so what happens here is the y's go away, and you're left with 2y minus 2y is 0, 2x minus 2x is 0, and negative 6 plus 2 is negative 4. And you're left with 0 equals negative 4. And you might think to yourself, that doesn't sound like a true statement. It's not. 0 can't ever be negative 4, which means at the very beginning of these problems, these two equations will never have a intersection point. They'll never have an x and a y value that align for both equations and match. There is no point that lies on both of those lines. There are individual points that lie on each line, but there's no point that lies on both of the lines. And so what this equation is, this is an inconsistent system. When you get does not equal like that, you get an inconsistent system. Or you might say no solution, because there's no solution for x comma y that would plug into both of those equations. All right, let's look at the other type, which you can probably guess if there's three different types. This is probably going to be the last one, which was the dependent system. Let's find out. What number should we multiply by to make things cancel? It looks like a positive 3 will do the trick, because I'm looking at these two terms and trying to make them cancel. And so if I rewrite that red equation, I'd get 3y minus 6x equals 15. And if I add the left side and add the right side, both sides of an equal sign, we'd get 0, because those two things cancel, 3y plus 3y, 6y and minus 6y cancel, and 15 minus 15 cancels, and so you get 0 equals 0. And what that means is we're not going to be able to find an x or a y, because for every single point on that graph, x and y are the same. These are the exact same two lines, just written in a slightly different way. And in fact, if you factor out a -1 from that red equation at the bottom, you'd see that these two lines are exactly the same. If you take that red equation and multiply by -1 on the left and the right, exact same line. And so these two systems have infinitely many solutions. In fact, every solution on that line, if you were to graph that line, either of them, every single point on that line is a solution. And we call that a dependent system. All right, we have one more problem where we're going to set up a word equation. And I'll probably set it up for you and then let you try to solve it on your own, but I'll help you with the setup. So you're going to a circus, and tickets cost a certain amount of money. So I'm going to color code this. For children, which I'm going to call C, they're $4. And for adults, which I'm going to call A, they're $12. And so what I know is I need to figure out how many children and how many adults there are. And it gives us a total number where it says 1,650 meal tickets were bought. And the total cost, which was $14,200. And so what I know is the easier equation of the two to set up would be if I'm going to label C as the number of children, and I'm going to label A as the number of adults, then I know from the total number of tickets sold that C plus A has to equal 1,650 tickets, because it's the number plus the number, and those are the only types of people that bought tickets. And now I'm going to use the price and just associate the number of people that bought a ticket with the price and say if C children bought tickets and they were $4 a piece, that means C times 4 is the total number that children spent, or the total price that children spent. And that means that 12 times A is the total cost of all the adults. Every adult spent $12, so if you had 6 adults, you'd multiply that by 12, and that's how much the adults spent. And if you combine those two numbers, you get the total cost for the whole night, which was $14,200. And now we've got a system of equations that we can solve. Sure, let's go ahead and just do it. What's going to make these terms cancel? It looks like if I multiply this by -4, those first two terms can cancel. And so that's what I'm going to do to both sides. I'm going to say my new line, if I'm just rewriting this line with the distributive property, is -4c minus 4a equals, what is 1,650 times -4? Let's see, 1,650 times 4 is 6,600. And it's negative because -4 was multiplied. All right, then I'm going to add both sides. So draw a line, put a plus sign, draw a line, put a plus sign, and we see those children cancel. The 4 children minus 4 children, we don't know anything about the children yet. But we do know that 8 adults, or $8 per adult, would turn into 14,200 minus 6,600, which is 7,600. And if we divide 7,600 by 8, we're left with 950. And what does that 950 represent? Because it's not the amount that the adults spent. We called A the number of adults. So there were 950 total adults. And again, let's pick the easiest equation to bring back down from the top. We said that C plus A, which is the number of children plus the number of adults, needed to equal 1650. That's a pretty easy one to plug and chug. So we're going to say the children plus, we know how many adults there were now, 950, has to equal 1650. And if we subtract 950 from both sides, we'll get the total number of children to be children equals 700. 50s cancel, and 16 minus 9 is 7. And so there were 700 total children. And what we just did is, given a total amount spent and a price per ticket and a total number of people, we figured out how many of each type of person there was, children and adults, when they never told us in the first place how many there was. Pretty cool. Pretty cool practical application of systems of linear equations. Because notice, nowhere in the problem did they say how many children showed up. They just said, hey, we made this much money and this many people came. How did we do that? And we found the exact answer. This is the only combination of children and adults that would result in that much money, 14,200, and exactly that many tickets, 1,650. All right, that's section 7.1. Thank you for watching. I'll see you next time for our very last notes video of the year. Congratulations on making it this far. Thanks for watching.